Okay, good morning, ladies and gentlemen. Welcome to the second day of RTCSA and NVMSA 2022. And we are very happy because today we have two outstanding speakers to give us the keynote speeches. And it's our honor to welcome David Xu, the FAE Director of ARM Taiwan, to give us a keynote speech. And the title is Overview of ARM Confidential Compute Architecture. Okay, because we are a bit behind the schedule, so I will not waste time. So let us hand over to David, and let us have a big hand to welcome David.
Thank you, Professor Huang. So let me switch to my notebook. Okay. Hi everyone. My name is David Xu, FA Director at ARM. So I'm delighted to be here to give you an overview of ARM confidential compute architecture. I think it's a new isolation technology for security. So before I go talk about confidential computing, so just let me give you a brief introduction about my company, just in case you're not familiar with ARM. Basically, ARM is IP provider. I don't know if you know what is IP means. It's intellectual properties. Basically we don't have manufacturer. We just provide our soft. How to say that? If you are in IC design field, it's more about like RTL code and the documentation to provide this to our partners to let them to develop their chip. Okay, so our our most famous of our IP is CPU, right? Especially the low power CPU. So our energy efficiency processors and the software platform have enabled advanced computing in 230 billion chip until now. So it's a huge number. I believe everyone here, you got ARM powered device in your hand. So I think our technology power product from tiny sensor to smartphone and even to high performance computing. So last year, there are around 29 billion ARM-based chip in the market. Okay, so I would like to say that ARM is most, the world's most pervasive computing platform, and our technology touches 30% of the world's population. So we believe where a compute happens, we will be there, and then we can advance it. So I think I just use 2 slides to give you a quick update about my companies. Hope you found it interesting. So now let's move to confidential computing. So what is confidential computing? I think confidential computing is a set of security standards which define the protection of data in use. Please note, it's data in use. It's very important. In a system, the data could be at rest, like inside memory. All data could be, in transit, like, transfer this data from this process unit to another processing unit. But the confidential compute is, mainly address the issue in data in use. When your data be accessed to, to be used to compute. So I think it's a key industry trend for security compute platform. So there are a lot of requirements driving the confidential compute. So let me just give you 2 examples. The first one is about AI machine learning's explosion. Right? It increased the use of sensitive and the private data for machine learning model. So the sensitive data is collected from like, I list in the slide like biometrics, health, shopping, fintech, etc. Right. So we have to have a mechanism to protect those private, sensitive data when it be used, no matter in client, no matter in cloud, or no matter in edge. So the second example to drive the computational computing is, is about more and more data protection regulations be created and implemented in different regions, which make computational compute even more crucial. Computational compute stack and the solution have been offered by a major cloud service provider, like Azure, Microsoft Azure's computational computing, Google's computational VMs, etc. So many of these have been discussed at a community called a Computational Compute Consortium. So where ARM is a member, but also a major cloud vendor like Google, like Facebook, Microsoft, they are also join the computational compute consortium. So in addition to ARM cloud service provider, we also got a lot of silicon partners, to join this community. So by the way, computational compute consortium is a project community at the Linux Foundation, dedicated and defining and accelerating the adoption of computational computing. So I mean, even right now, a lot of companies, they also want to join the computational computing consortiums since, they have a computational compute stack software they want to offer to the industry. So computational compute, basically, it provides a trustworthy hardware-backed secure environment and can be applied to all segments, right? So I'll just give you some example, like, in mobile, PC use case, the company's email, right, can be isolated, from other applications like social media browsing, under computational compute architecture. And then in cloud service, in a cloud, there are a lot of, tenants, existing in a, single compute system. So how can you, guarantee that the tenants in between tenants, they can protect from each other, right? Once you apply computational compute, he can help, he can offer you such a security environment. So in automotive use case, drivers' personal data is protected from like OEMs applications and autonomous drive systems access, etc. So I think I just give you a concept what is about computational computing. So in the following slides, I'm going to talk about what ARM offer, what is ARM's computational compute architecture. So I just give you some background about ARM computational compute architecture. So it's introduced as the supplement of ARM v9.2 architecture. So ARM's architecture is a kind of generation evolution, right? We got ARM 7, Cortex, ARM 9, ARM 15, ARM 76, etc. Right? The architecture I mean is instruction set architecture. It's evolution generation by generation. So right now the latest architecture is the 9th generation. Right? We just launched our V9 architecture last year. So the computational compute architecture, it's a supplement, in V9.2. Yeah, and we just announced computational compute architecture in March last year, and the first specification is released public in June last year. So why we to put a computational compute in our latest instruction set architecture? I think it's driving by expanding the need of privacy and security. So I will talk about more about this part later. So on CCA, computational compute architecture protects all data and the code where computing happens. So protect data in use by preventing privilege access the resource, whilst retaining the right to manage them. I think that's a key point in computational compute. This one. I mean, traditionally, the computer system or a processor, the higher privilege software, they can manage the lower privilege software, and also to access the lower privilege software's resource and memory. However, in computational compute, it changes. The higher privilege software can only manage the low privilege software's resource or memory, but cannot access. That's the way computational compute to achieve even more robust in security. Yeah, so as I mentioned, in traditional compute architecture, we give the right to kernel, like operating system, to manage the processor and resource, but also give the right to access the resource, But the idea of CCA is to remove the right of access, just keep the right to manage, to kernel or lower layer hypervisor. So, in ARM architectures, we provide a numbers of different isolation technology over a year. So we start with trust zone. I think it's quite famous, in a mobile phone system. So it provides the environment protected from host OS and the hypervisor. So this technology is designed to be used by device vendor or silicon vendor, to provide platform security use case. With Lightweight, it tends to be developed with trusted OS and SDK associated with the devices. So in trust zone, there's no way to dynamically make memory to be trust zone protect memory, versus standard memory used by process. The memory used by trust zone is conducted at boot time, right? So you cannot dynamically to change the memory's attribute in runtime. So it's limited in resource in trust zone. Next is about virtualization. Virtualization is another technology. It can be used to protect a virtual machine from host operating system. So an example is, like a Microsoft virtualization-based security. It put your password and the confidential information into a separate virtual memory from the main operating system, which you interact with. So with virtualization, you do have dynamic scheme to take a page memory, move to a virtual machine for security use case, or using a regular host operating system for other application processes. Trust zone does not have such dynamic. A virtual machine has to trust hypervisor, and it has to trust all the trust zone, because trust zone code can be accessed, not secure, physical address where the hypervisor kernel, application, etc. are running. I will explain the detail, about the physical address space and the security state later. So the third one is about secure EL2. I think before on architecture V8.4, there's no perceived need for multiple virtual machine in secure security state. So this means that support for virtualization in secure security state was not necessary. So as on trust zone adoption increased, so some trust service were tied to specific trust kernels. For a device to support multiple services, it might need to run multiple trusted kernels. So we introduced secure virtualization, which is supposed for EL2 in secure state, comes with V8.4. Yeah, simply speaking, secure EL2, is just make that in secure state, it can support virtual machine. So, basically, in ARMS, like a V8 processor or V7 processor, in a processor, you got two states. One is secure security state. The other one is non-secure security state. So before V8.4, so only a virtual hypervisor, I would say like a virtual machine can only be supported in non-secure state. Right. But after V8.4, we start to support virtual machine in secure state. So the last one is on confidential compute architecture. It tries to combine all the good manners and remove some limitation from previous effort in this area. So on confidential compute architecture, introduce a new confidential compute environment, protect from host, OS, hypervisor, and trust zone. Just as I mentioned, if you run an app, this app cannot be accessed by host, OS, hypervisor, and even trust zone if this application is put in wrong state. Right. I will talk about the security state later. Yeah. So just give you your idea, right? That in CCA, in confidential compute architecture, the app in ROM cannot be accessed by hypervisor or operating system, but it still be managed by OS and the hypervisor. Okay, so that's the isolation solution provide in our product until now. So what drive the confidential compute architecture? I think it's driven by the requirement. Right. So the first requirement is about the minimal chain of trust. So an application only need to trust itself. I mean, even as I mentioned, even hypervisor, even operating system, you don't need to trust them. So it does not need to trust like even like in addition to host operating system and hypervisor, you don't even not need to trust CCA hardware engines. So regardless of the privilege level. So in ARM v9, so we define a role management extension. So it's a hard way to implement ARM confidential compute architecture. So role management extension is quite important. So in my presentation, I will spend more time to explain the role management extension later. So I think the role it defines new isolation boundary, right? So role content cannot be accessed by other role and host OS hypervisor or even by trust zone. The second requirement to drive the confidential compute is about a scale. So we don't want it to be limited in resource. So we want it to, confidential compute architecture is more like virtualization. So memory page can be used for running secure execution environment. So in ARM confidential compute architecture, it provides dynamic memory mechanism. So you can take a page, use it either for ROM or non-secure hypervisor application or trust zone. So we also want to have standard programming model, to make the software develop easy, easy to develop in their software. So we define standard API on binary interface to manage ROMs. A testable is very important to a confidential compute architecture system. I think it's about a system where something produces evidence like about itself, like other parties can evaluate the trustworthiness to access. Right? When you run a system, you have to ensure the system is secure, and you have to ensure the environment you are located is secure enough. We use the attestation report to guarantee this. So basically, a attestation allows the ROM owner to establish and evaluate trust in the ROM before provisioning any secret to it. Code running inside ROM will manage confidential data or run confidential algorithms. Therefore, the code need to be sure it's running at real CCA platform, but not, run on a simulation or emulation. Because I think a simulation or emulation is very weak. It could be attacked by hacker. So to address this, we define system hardware architecture and a binary interface specs to support attestation for ROM. Okay, what is ROM? So ROM basically is a virtual machine. It's protected virtual machine, similar to other confidential compute like AMD's SEV, SMP, and Intel TDX. We take a virtual machine, run it on the other side. It's create this ROM. Basically, it's a protect virtual machine. We create it and run on the other side, right? With isolation boundary. So the ROM run here can be protected. Yeah, I will talk the detail later. So I just give you some example about what ROM is. That in a data center, a ROM could be like a protected customer virtual machine, or it could be a cloud service instance. So in mobile client system, the ROM could be a protected client application or application service. So the ROM execution and memory access are initiated by the controlling host software, like an example is hypervisor. So this ROM controlled and managed by this hypervisor, but this hypervisor cannot access this ROM. So the ROM has an independent chain of trust from those used by the normal and the secure worlds. The ROM is also completely isolated from controlling software like operating system or hypervisor. If a ROM is initiated by a host, the host has no ability to see the data or code of the ROM. Yeah, I keep emphasizing this point. Right? The host software can control and manage this ROM, but this host software cannot access the ROM. So in ROM management extension, we defined two approaches for memory protection. The first one is isolation, The isolation is a hardware enforced mechanism through the architecture ROM management extension, which allow control over memory management, execution, and the isolation of the ROM or context and the data. Isolation means that invalid access in preventing through faulting exception by the processing element. That means that if a hypervisor, for example, it try to access the memory, for ROMs, it will generate an exception. So I think in addition to isolation, I think a ROM management extension also, define encryption. A ROM-enabled system, the minimum requirement is to, use a separate, encryption methodology to protect the external memory. So it can use a separate encryption key or trick for each physical address space. So the encryption is mainly prevent for reboot attack. And the isolation technology defined in CCA on computational computer architecture, is not only applied to the processor, but also, can be applied to DMA through the system MAU. I'm not sure if you are familiar with MAU. Basically, MAU has two major functions. The one is to do memory protection. The other one is to do the virtual address to physical address translation. So in terms of the threat model, so ROM primary is confidentiality and integrity architecture. It protects against some read or modification by our ROM, hypervisor, kernel, threshold, and even device that ROM does not trust. Yeah. So I think the confidentiality means that someone, if they don't got access right, but it can, trying to access a protected memory, to read the protected memory. It's about confidentiality. A similar behavior, if you want to try to modify the private memory resources, it's about integrity. So ROM basically is, can protect its behavior like confidentiality and integrity. But ROM does not have availability guarantee, right? Availability guarantee is more like a scheduling. It's done by operating system or hypervisor. Yeah, and the scheduling is very complicated mechanism. We don't want to define new architecture, something like a CCA to mess it up. So in addition to confidentiality and the integrity, CCA also protect against indirect software attack. But we do expect software code running in a ROM does use the protection stuff we added in architecture over the years, such as barrier instruction and how speculation can be used in the implementation. So there's nothing in the architecture, does specify the protection against direct hardware attack, such as a physical DRM prop or replay. This is in the scope for particular products, and the silicon vendor or device vendor need to be make some additional protections. So on confidential compute architecture platform come together through a mix of hardware additions and the firmware components. So in today's section, I'm going to focus, more on like the hardware, additional hardware part, I already mentioned many times, like a role management extension. So like how we define in our new confidential computer architecture. Right. So on the following slide, I'm going to go through a detail about how role management extension works. So I think in the following slides will be more technical and maybe more tough or difficult to to understand. But if you have any question, feel free to ask. So let's start. In order to build a whole picture about how computational compute work, let me start from just from some fundamental stuff. It's about privilege and the address translation. So it's a very just a very simple processor without any extra we call it security states. Only single state, just normal we'll call it normal wall or non-secure state. In this architecture, just like most of the other architecture, I think we define different levels of privilege. We got exception level 0, exception level 1, and exception level 2. So the high level software applications, it's running on exception level 0. And for the operating system, its kernel, it's running on exception level 2. Exception level 1. And the hypervisor, right, it's running on exception level 2. So higher exception levels have the privilege to access register that control lower levels. The current level of privilege can only change when the process take or return from an exception or interrupt. So if you are running a virtual machine, so you will see a two-stage address translator. So it's done by MMU, memory management unit. So the stage 1 translation is is mainly to translate virtual address to intermediate physical address, which is done by operating system. And the stage 2 translation, it's translate intermediate physical address to physical address, which is done by the hypervisor. Okay, so that's just a foundation. You just need to remember the privilege level and the address translation. So with trust zone, right? On privilege stage, you can only see the left-hand side architecture. But with trust zone, we got additional, we call it security state. So with trust zone, we got the 2 security state. The first one is non-secure security state. The second one is a secure security state. And we also define 2 address spaces. The first one is secure physical address space. Another one is non-secure physical address space. So basically, trust zone, trust zone define these 2 elements to achieve security and isolation. So when you are in a non-secure security state, you can only access a memory location which which belong to non-secure physical address space. But if you are in a trust zone, you can access both non-secure physical address and the secure physical address. So the isolation boundary is based on security state. Let's start it line. And there is additional exception label created for trust zone. It's EL3, exception label 3, which is used mainly to switch between security state. So you can see that in this picture, we got one more exception label. It's EL3. So as I mentioned, trust zone does not support dynamic memory. That means that memory location cannot be moved between secure and non-secure physical address. Memory for secure physical address is typically statically parked. Just as I mentioned previously, trust zone have to be defined in a good time. Yeah, you cannot do it to dynamic change the memory in running time, in runtime. So you can have an application run on non-secure EL0, then the application can request to have secure service through secure Monicode or hardware exception McKinney, and end up to be in secure exception level 0. So with role management, there are more. We got more security state, and more address space, So with role management extension, the 2 additional security state and the physical address space are added to support. There are a wrong state, wrong physical address space, and the root state and the root physical address space. So you can see that the upside picture, it describes that there additional security state, be added, in the architecture, in the system. Right? It's here it's a wrong security state and root security state. So this table describes, in which security state, you are be allowed to access what physical address space. Like the new security state wrong, it can access non-secure physical address space, wrong physical address space. And for root, it can access all the physical address space. Okay, so basically, trust zone, a secure state and the wrong state, they are mutually distrusting. They don't trust each other, which means that a wrong cannot access secure physical address, and the trust zone running on a secure security state cannot access wrong physical address space. So the root state, we run a software, we call it Monit. It creates its own security state, its root state, and its own physical address space, its root physical address space. So in trust zone, the monitor is even though in the most. So in trust zone, there's also a monitor, right? But you can find that in trust zone, the monitor they don't have layer of security state. It's in the secure security state, same as the rest of the trust zone component. But in CCA, computational computer architecture, we create addition security state for monitoring. So that's different, from trust zone. only system. Okay. In addition to new security state and the physical address space, so we also added some like mechanic and data structure to achieve dynamic memory function. So as I mentioned, compared to trust zone, dynamic memory is a key feature in role management extension. So it provides a mechanism to dynamic allocate pages to different physical address space at runtime. So for example, when starting a role, ownership of some memory is transferred from non-secure state to wrong state. And the memory region becomes wrong physical address space. When the wrong is terminated, the memory is declared and the owner returns to a non-secure state. The raw memory region released and it changed back to non-secure physical address space. Right, so in RAW, the dynamic memory is doable now. So to enable the dynamic assign a memory region between different physical address space, we bring a mechanism, we call it granular protection check, in role management extension. So concept-wise, granular protection check is performed in the MNU after stage 1 and stage 2 address translation. The MNU only permit the access where the output physical address space from virtual address to physical address translation match the physical address space recorded in granular protection tables. So granular protection table is a new data structure. It configures which physical address space each granule is associated with. When the processor performs access, the MMU works the granular protection table to determine whether the access is permitted. If the physical address space does not match, the MMU block the access and return a granular protection fault. It's an exception. Okay. So now let's just put it together, to show how CCA works. So basically, in a processor, you will see there are multiple CPU inside, and there are also after downside the CPU layer, memory management unit (MMU), and it do like a two-stage address translation. So in this system, MMU extend the page table used to protect ROM from each other. So the standard stage 2 isolation provided by MMU and the system MMU. I mean, in a system, you may not only have CPU, but you have other hardware engines like DMA. So you can also to isolate, to protect DMA data in use by put the system MMU here. So I mean stage 2 translation MMU is the purpose is to protect the ROM from each other. So one ROM cannot access other ROMs like memory location. It's achieved by stage 2 translation MMU. And when the MMU resolve the virtual address to physical address, and you want to protect between different physical address space by considering the security state you are running, a granular protection check coming. It provides a kind of isolation from different physical address space. Right. So if you want to protect a ROM from each other, you use MMU's stage 2 address translation. But if you want to protect the ROM from different from different software, like host software, like hypervisor operating system in other, security state, it's performed by granular protection check. And in addition to like isolation, right? As I mentioned, ROM, for ROM enabled system, the baseline encryption requirement is to support encryption for external memory like DRAM, right? So this is an example that you have to do like encryption decryption function inside your memory controller. So when store data, so we put it together. When store data to DRAM, the data flow is down direction, right? When store data to DRAM, the encryption happens in memory controller. So on the other hand, when data access from DRAM, to SoC, a chip, the data is decrypted by the memory controller. So memory beyond the SoC is encrypted. This is SoC. Memory beyond SoC is encrypted. And memory in SoC is plain text. So memory data in SoC is plain text, but it's protected by isolation boundaries. So that's the way, we to protect data in use. So with ARM computational computer architecture, we have secure world with secure security state to run trust zone workload, and we introduce a new role specific to run third-party applications, the third-party virtual machines. So ARM CCA consists of a hardware and firmware component. So role management extension is a hardware component provide isolation primitive as introduced with previous slides. The firmware component introducing role management monitor and the monitor. Here is a role management monitor and the monitor. So role management monitor basically is running on exception level 2 in role security state, EL2 in role security state. It manages role execution environments and the inter-role isolation. So monitor is running on exception level 3. In root security state, it got its own security state. We call it ROM security state. It manages context switch between security state. So the main function of monitor is to in charge of the context switch between different security states. So here are some published on computational computer architecture resources. It include some like spec documentation and even some presentation video. So I think that's my last slide. So that brings me to the end of my presentation. So thank you for your attention.
Thank you so much for the great talk. Although we are almost running out of our time, but I would still ask if there is any questions regarding okay. Sorry, we have quiet.
Okay, so thanks for a nice talk and tutorial. So you mentioned about the CCA for in architecture level. How about the microarchitecture? So if the microarchitecture screws up all the stuff like in meltdown inspectory, then the CCA would also be completely broken. What does the microarchitecture have to provide and be certified to meet your CCA requirement?
Okay, yeah, thank you. A good question. Yeah. You know, normally we will release, as I mentioned, it's a instruction set architecture, you know, right before our real processor be, you know, launched in the market, right? So, I think one answer to your question is, you know, for the microarchitecture implementation, we are going to, you know, target in our data center and the server CPU first. I'm not sure if you heard about Neoverse family processor. We are going to deploy it on CCA architecture in, you know, standard product. I mean, for the data center and the server CPU. The other question, you know, how to guarantee the CCA, you know, be implement and you know, guarantee that it's follow our architecture. I think there are many things to do when we do, you know, a CPU develop for validation and verification. You know, I am not expert for that, but you know, if you remember, I mentioned that attestation, right? A ROM can, you know, actually we define kind of, you know, like, you know, architecture or component to, you know, to verify if they are in a secure, like a CCA environment. So a ROM, you know, if in a real CPU, in a real microarchitecture implement CPU, a ROM can request to generate the report to evaluate if they are in a, you know, real CCA platform anytime. So I think that's the way, you know, we to guarantee that the ROM is in a secure environment. Does that answer your question? Okay. Thank you.
Thank you very much. And because of the time is running out, maybe we have a big hand to thank the speaker again. Furthermore, we have certificates for thanking David for this great talk. Thank you very much.